So the main result I want to discuss gives you a lower bound for, so it's easy to get upper bounds for the class. You just have to exhibit some filtration, some flag on the differential module. The difficult thing is to show that what you construct is the most optimal. So what you're looking for is lower bounds, and that's addressed by the next result here. So this is the class inequality, which is supposed to be the topic of today's lecture. Right. So this is in this paper with Abramo and Buchweitz, the first one I mentioned. And the hypothesis, now we are going into the commutative world. So R is a commutative Noetherian ring, and I have to assume that it contains a field. I will discuss the proof, so then you'll see where this hypothesis comes in. So R is now a commutative Noetherian ring containing a field. So for example, a polynomial ring or a quotient of a polynomial ring over a field. Okay. Now, and F is a differential module which is finitely generated. F which is finitely generated as an R module. Okay. And then the result is, so this is just the hypothesis, then the result is that then for any differential module D which is a direct summand of F, as a differential module. So what another way of saying it is that D is a retract of F. So one has an inequality, and of course I want to assume that the homology of this differential module is not 0. The class of F class of F is, and this term that comes up here will be familiar now, it's the height of the annihilator of D plus, that's it, it's the height of the annihilator of D. So this is an R module, this is the ideal of elements in R which kills this module, so it's the annihilator module, and I'm looking at the height of this module. So in particular, this applies, of course, you can take D to be F itself. You get this result. So let me put it up here. Too bad. Maybe I should bring it down first. So this is the result. It's a little bit more technical than what we had for the perfect complexes, but this generality is required. So you do have to worry about summands of differential modules, because it could be, for example, that the class of a direct summand could be infinite. So if a differential module has a flag, there's no guarantee that a direct summand would have a flag. See, unlike, again, this is the distinction between perfect complexes and differential module, complexes and differential module. If you have a perfect complex, and if you have a direct summand of the perfect complex, it's still perfect, right? But that may not be true for differential module. So you do have to work with this generality. That's why this comes in. So just at least for the moment, just look at this inequality here. It is an inequality like the one we discussed yesterday, you're giving a lower bound for some invariant of interest in terms of the homology. And from what we have been discussing so far concerning perfect complexes, it's clear that this, no, that's why. It's clear that it implies the new intersection theorem, but only for rings containing fields. So as a corollary, one gets the new intersection theorem only for rings containing fields. So let me in fact remind you what it is. Not everyone was here yesterday. So if you take a perfect complex, then so the class of the corresponding differential module, according to this the class inequality here, this is bigger than the height of the annihilator of the homology of this differential module. But this is of course just the homology of P. Yeah? And on the other hand, this estimate here told you that this is at least no more than B minus A. So this inequality, that the number of non-zero modules here in the perfect complex is at least the height, that is the new intersection theorem. And that's the proof. So this does contain the new intersection theorem. It also gives you an estimate for, it also contains a theorem for differential modules over graded algebras. I'll get to that in the end, and that's really important for my next lecture, tomorrow's lecture. So let me not get into that. Let me now, in fact, illustrate this by computing the class of the scorpion. If you look at the class of, remember this thing here, this module that we had, so the class of this is at least, and so the ring here is kxy. And it's not so hard to check that the homology of this is just k. So it is as if you did not add this differential at all. So if you just ignore this, the homology is k, because it's the Koszul complex. But even if you add this, the homology still stays the same. All you have done is that you've identified this cycle with something here by adding this element here, by the image of this. So the homology is still k. So it's the height of the annihilator of S but this is k, and the annihilator of k is xy. And Kiriko computed the height of this example for us yesterday on the board, for some of us anyway. That's 2.